Yeah, good afternoon, everyone. Today I'll be presenting RegionCLIP, region-based language image pre-training. It's from CVPR 2022. Yeah, let's get started.
Yes. Share the screen.
Yeah. This is share screen and hopefully recording. Okay, yeah. So with the advancement in the vision language representation learning, we got the models such as CLIP and Align, and these models can be extended toward like image classification and achieve some good results without in the image without labels. And but the author of this paper asks that how does these models perform on the if some region of the image is given. Like in the case of object detection, we have a bounding box, and we don't have the whole image. So they want to test this, and they constructed a simple RCNN style object detectors, and they use Pretraining clip, and they find out that like initially the accuracy of the clip in the ImageNet is around 60%, but when they give the region of the image to the clip, the accuracy drops very low in this data set. But if you increase the bounding box, the detection accuracy will get higher. So this means that like these clip models, they don't perform good when the region of the image are given. So the question they ask is that how can we empower the vision language pre-trained model to reason about image region? So they want to make the clip type model to focus on the regions of the image, and they deduct that the problem can be in the training of the vision language models.
Yes, I realized that we start already. So this is 213. So anyways,
yeah. So while training the clip model, usually the model tries to match the text to the whole image, and there is no alignment between the text tokens and the image regions. And so they wanted to change this, but there is some challenge to this. Like in training in this manner, they require when training in the clip type manner, the surrounding features can be used for the detection or classification. So when you want to match the text tokens with the image region, you may lose this uppercase, and also training in this manner require high computation. So they need to tackle this challenge to overcome these problems. So they propose the text encoder and image region. So their solution is to align the text tokens and image regions during the pre-training. But also for this, they need there is not many data set that has each of the region of the image and their text tokens. Like as we have like for the clip, there is data set that has image and text pairs, but for the regions, we don't have it. And also for each image in the data set that are clip are trained, in those data set, the text that provided for each image, they do not describe all part of the image. Like for example, here in the data set, the text for this image is given: a boy is flying a kite, but there is also cruise and the bike. So yeah, so the roughly overview of their method is that for each region of the image provided by some backbone, they get the text using pre-trained clip, and save it as a pseudo label for each region, and then train their model using this. Okay, we'll go deep into this later. So here's the overview of their method. So in the first part, it's like the normal clip. They just train it in the large data set. And they have like a text encoder and a visual encoder. And then the second part is their pre-training. So here they get the image regions, and then also they try to get as much, they make the concept pool, they get this as much, so like extract this key feature from the text that describe the image. So usually this image, they have like a long description. So like the boy is flying a kite, the people walking by bus. So here they get the boy and the kite, and then using they fill the multiple prompts so that they make the region description. So they make the prompts, and then they feed these prompts into the language encoder from the pre-trained clip so that they get the distribution for concept distillation. And also they feed the cropped regions into the clip visual encoder, and they pair these regions and then this region and these prompts, and then they use this to train their own visual encoder.
But, are they manually labeling that?
No, this is done. This is done using the clip pre-training visual and label. So we're going deeper into this later. So like this is kind of overview. So yeah, so the definition, the problem definition for them is that the goal is to create a system that understand and interpret regions within an image, similar to human understanding language. And this approach allows the system not just detect objects, but also understand them in semantically rich way, similar to human might describe them. So in other words, they want to build visual semantic space for region of the image. So like given the description of the description for a region of the image I, in the visual semantic space, the vision region extracted from the visual region extracted from the given region of the image should match the language representation. So here V stands for visual encoder and L stands for language encoder. So here they're talking about this part. So yeah, so they want to train a visual encoder that can encode the image regions and make them to the description encoder through the language encoders. And so yeah, as I said earlier, for training these visual encoders, they first create a concept pool and then make them into the several prompts. Like for each word, there is several prompts. And okay, I think this image should not be here. Okay, so for the visual region representation, how do they get these image regions? So image regions can be proposed by object localizers such as RPN or the dense sliding windows, so the random regions. In this paper, they use RPM pre-trained on the human annotated bounding box without labels. And the RPN proposed n image regions denoted as RI. And for each region, its visual representation is extracted from the visual encoder using ROI align. So this ROI align pulls regional visual features from feature map, from the whole image feature map using interpolation. And so during the training, they first initialize this visual encoder from the pre-trained clip encoder. It's not good for image regions, but it's it's good for starting. So it will be very good for starting point. And for semantic regions, for the prompts, so usually it's really hard to annotate every object in the image, which can be around a lot of classes, maybe up to thousands. So what they do is that they make the pool of concepts, and then that covers original concepts. And these words are extracted from the descriptions using the language parser. And then also given these full concepts, they make the prompts. And then these prompts are fed into the pre-trained CLIP language encoder, and they get, and then also using the pre-trained CLIP visual encoders, they get some values for which prompt best describe which region. And then, yeah. So they use the pre-trained CLIP visual encoder to correspond between image regions and the prompts that we made from the concept pool. And then they compute the matching score, and then they pair to like the region and the prompt which had the highest matching score. And that's how they make the pseudo labels. And then they do pre-training to train their own visual and regional visual encoder. And so this is the constructive loss they calculate between each prompt and the region. So in this loss, they also take into account the matching between the, like here, as you can see, like this prompt best describe the first region, and this prompt best describe the last, something like that. So this one doesn't, like the other prompts, like for the boy, there is several other prompts which doesn't describe them in the, like doesn't match with the region that much. But during this loss, they also take those into account. And they argue that this can be helpful when the regional visual encoder will be used for the novel classes, the unseen classes. And also they use knowledge distillation for each image region and all object concepts. So here they use KL divergence between the two probabilities. So here QT and QI are these probabilities made by language encoder. And also this constructive loss is for the region, but they extend it toward the image level. So they just say that like image is one object, and then they apply the same. So like here it's applied toward each regions, but they just extend it a little bit and say that image is only one region, and the description that are ground truths for that image is a prompt, and they calculate this constructive image loss, and then their final loss is the summation of the all losses. So after pre-training, they can transfer their model toward the object detection. So like usually these labels made by the CLIP for the each region are noisy, a little bit noisy. They are so when there is some data set available with the labels of each region, then this model will perform much better. And also, yeah, they also train for open vocabulary object detection. Yeah, so they train the visual encoder on the annotation of base categories, and then they expect to detect the novel unseen categories on the data set. So for this, they apply class-wise weight cross entropy loss to train the detectors. And they argue that this cross entropy this loss is inspired by focal loss, so that in the case when there is some base cases with very few data, like, and then this loss may help the model to not forget about this kind of base cases with a few data in them, and also prevent it from the overfitting with a small set of the base categories. Okay, yeah, so data set they used are as follow. So for pre-training clip, they use CCM, which has 3 million of the image and text pairs. So they and also there is COCO caption, which used to pre-train the model for conducting ablation study. This is a smaller data set, so the training will not take that much time. And also, as we said, they get the prompts using the concept pools. So they parse the object concepts from these data sets, and then they filter each word with frequency lower than 100. And yeah, they get around 10,000 concepts for each data set. Yeah, for the open vocabulary object detection, they trained their model on the base cases of the COCO and LBIS data set. So the COCO has 48 base category and 17 novel category. So this kind of unseen categories, and this is categories that they will train. And same goes for LBIS, which is much bigger data set. And these novel categories are rare objects, and these base categories are common and frequent objects in the data set. This is how they divide them. And yeah, so here are the results. So currently the state of the art model in the COCO dataset is OVR, but as you can see, the results of this RegionCLIP is higher in all cases. And this model, VILD, it's not published anywhere, and they use some kind of very complex training strategy, and that's how they get like better results in these categories. But when this RegionCLIP increases they change their backbone and increase the size of the backbone, and then train for a little bit more, then they get much better results and achieve state of the art in all categories. So this is the results of open vocabulary object detection on LBIS dataset. So forgot about this. I think here APR stands for the base cases, and APC and APF stands for novel cases. No, yeah, so it's opposite. So APR is a novel case, the cases that the model didn't see for while training, and APC and APF are the categories that the model is trained on. So as we said here, so yeah, there are like 866 base categories that the model will be trained on, and 377 novel categories. So yeah, as you can see, they achieve really good results on unseen categories. And also for fully supervised object detection on COCO and this data set. The results are state of the art. So they use their pre-trained visual encoder here, and they said that like our detector initialized by pre-trained visual encoder converge faster and significantly outperform the pre-trained backbone on ImageNet and CLIP. Here is also, they did zero-shot inference for object detection. So when they use grounding bounding boxes, of course, the result would be much higher, and their result is better than others. So when they use RPN here, for region proposal, they still get the best result, but it's much lower than the ground truth. Those data sets. So for the ablation study, they did 4 ablation studies. First, they did ablation study on the region text pairs, which they got from the clip, and then the image text pair, which is ground truth. And here, just this region text pair already gives some good results. But of course, if you add the ground truth pairs, they get a little bit higher result, but not that much. And yeah, for this ablation study, the model was trained on the smaller data set. So yeah, so they did the same ablation study for region type like random and RPN. So here, yeah, this is an ablation study on the pre-training data sets and the source of the concept pool. So the concept pool, that word that used for making the prompts. And as you can see, when pre-training on CC 3 million data set, and then the concept pool I get from COCO-CAP, this part get the highest, this outperform all other methods. And they claim this because this data set has much more data, and then the description of the image in this COCO-CAP data set is better, I think. Okay, then also for losses, they did this. They did the ablation study, which includes one of the loss or the both of them combined. And when you have the both losses, you get a better result in overall. And this is all.
But which year this paper was published?
I think it's CVPR 22.
Paper is quite old. So I know that there are more recent papers in this stream of words.
Yep, I think yeah.
And I think it's better to read such.